Hi, in this video I want to talk about how we can create an electric field using magnetic fields and the physical motion of an object. So when I talked about the Hall example, I mentioned that if I have moving charges in a wire because of a current and I place that object in a magnetic field, there'll be a magnetic force causing the charges to want to move to one side of the wire, so eventually an electric field would build up, canceling out that magnetic force. Well, a loop of wire is just a chunk of metal, and if you start running with it, you have essentially a current. Charges that are freely moving, even though it's not the way we conventionally think about how currents work. Well, if I were to look at the magnetic force on a moving charge would be my charge times the velocity of the charge times the strength of my magnetic field times the sine of the angle between the motion of the charge and the magnetic field. So to make our lives simple, let's assume that we set everything up so that that wire is moving perpendicular to any magnetic field that we have. Well, there would be a magnetic force, and those electrons would get pushed down in that wire, so we'd build up a region of negative charge towards the bottom of the wire, a region of positive charge towards the top of the wire, so that difference in charge creates an electric field from the positive to negative charges. And those charges will continue to move until the electric force is the same size as the magnetic force. So, for an electric force, it's equal to the charge times the strength of the electric field. And for the case of uniform electric fields, and what we would see in this wire would be a uniform drop in electric field, uniform electric fields have a value equal to the change in electric potential from one end of the object to the other divided by the length of that object. So my forces have to be equal. Charge is irrelevant, so that means my electric field has to be equal to the speed of the wire times the magnetic field. So my change in electric potential would be equal to the speed of my wire times the length of my wire times the strength of the magnetic field that it's moving perpendicular to. So if it's moving along a magnetic field line, we don't get any change in potential. So let's say that we have a child who's flying a kite with a steel string, and the steel string is 100 meters long. And the child's going to be running at a speed of 4 meters per second, and they're going to be running, and they'll just happen to be running so that that kite string is making a 90-degree angle with its motion compared to Earth's magnetic field. So we'll get the full effect of the strength of Earth's magnetic field, 5 times 10 to the minus 5 Tesla. So in that case, the potential difference on that kite string is going to be 4 meters per second times 100 meters, which gives me 400, times 5 times 10 to the negative 5 Tesla. That gives me a potential difference of only 0.02 volts. So not an effective way of generating electrical energy. However, we're dealing with a pretty slow speed here. You increase that speed to something of a couple hundred meters per second, like an aircraft, and you start getting a more significant potential difference that can form over the surface of that aircraft. You have a dangling cord on something going even faster, like an orbiting space probe traveling at 8,000 meters per second. You can start getting some pretty significant potential differences if you end up trailing an incredibly long cable from a satellite. So these are some real-world considerations that people in aerospace take into account when they're trying to figure out and design, is this craft going to be safe? Is any electronic equipment inside going to be protected from any possible stray generated electrical signals? Thanks for watching.